All right, this is 12.2a, test for homogeneity and independence in a two-way table. All right, so this is our second chi-square test after we did our goodness of fit test from lesson 1. So this one, also categorical variables. This time, however, we have two categorical variables when we want to do a test for homogeneity. All right, so let's get started. So we got a null hypothesis for our chi-square test for homogeneity. The null hypothesis is always going to be about the distributions being the same for a bunch of different groups. All right, so the distribution is the same, so it's homogeneous for all the different groups. And you can put this in more context once you're given a problem. Different groups. All right, so your null hypothesis is always that they are going to be the same. And so the alternative hypothesis is that the distribution is not the same or is different. All right, so the distribution is not the same for all the different groups. All right, so that's going to be our null and alternative hypothesis. We're testing to see whether or not the distribution of something is the same across a number of groups. All right, now next, the conditions. The good thing is that for chi-square tests, all the conditions are going to be the same. All right, so the same as yesterday. We're going to use our acronym RAD. So random sample or random assignment, depending on the problem. Number 2, all expected cell frequencies need to be at least 5. And we do actually have to check that. We can't just assume. And then lastly, data are in counts. So making sure our variable is categorical and we're just counting how many things pop up in each category. All right, so those conditions are the same. All right, next are expected cell counts. So for this one, we have a formula to find the expected cell counts. And for each cell, you're going to do the row total times the column total divided by the total or grand total. Okay, so let me see if I can do a quick example to show you what that means. So let's say I wanted to see if political standing is the same across all the grade levels. So we got, let's say Democrat, Republican, and we'll just do other for simplicity. And then let's say we have freshmen, sophomores, juniors, and seniors. All right, I'm just going to make up some numbers here. And so let's say we have, 2, 5, 10, let's say 8, 1, 2, 3, 4, 6, 7, 0, 1. All right. So if those are my counts, if I wanted to, let's say, find the expected, so these are my observed counts, the one in yellow. If I wanted to find the expected counts, let's say for this cell, Democrat freshman, I would take the total of the row, so that gets me 20 when I add these guys up. I take the total of the column, and that gets me 17. And then just the overall total of everybody. So let me do that quickly here. Oh, so this turns out to be 10. This is 19, so that gets me a total of 49. All right, So I have a total of 49. So to find the expected counts, let's say in blue here, for that cell, I would do 20, so I'll call this expected, 20 times 17 over 49. All right, and that gets me 6.939. All right, so the expected counts would be 6.939 for that one. Let's say I wanted to do junior Republican. All right, so expected for Republican juniors. Then I would do the row total, which is 10, times the column total, which is 13, divided by the total of 49. All right, and that gets me 2.65. All right, so that would be the expected count for that one. All right, so that's how you would find the expected counts for each of those cells, and we want to make sure that all those are at least 5 to meet condition number 2. All right, now there is a faster way to do that on your calculator, which I will explain to you later. Okay, let's go to degrees of freedom. Degrees of freedom, this is going to be your number of rows, so number of rows, minus 1, times the number of columns, minus 1. All right, so then in our example here, we had 3 rows and 4 columns. All right, so in this example, we would do 2 times 3, which gets us 6 degrees of freedom. So this guy would have 6 degrees of freedom. So number of columns, number of rows, subtract 1, we got 2 times 3, which gets us 6. All right, and that's how you find degrees of freedom. Okay. And then our chi-square is going to be the same as yesterday, observed minus expected square, all over expected. And the p-value, just remember, is always the area to the right of that chi-square we find. All right, in our chi-square model. Okay, let's go ahead and give this a try. All right, so the question is example 1. A study was conducted to determine if collegiate soccer players had an increased risk of concussions over other athletes or students. The two-way frequency table, also known as a contingency table, below displays the number of previous concussions for students in independently selected random samples of 91 soccer players, 96 non-soccer athletes, and 53 non-athletes. All right, so they want to see if the distribution of concussions is the same across these 3 groups or if it's different. All right, so we're going to go ahead and start with our null and alternative hypothesis. Okay, so we got our null hypothesis and our alternative hypothesis. So I'm going to start with the null in that the distribution, I'm going to put more context in here, of concussions is the same for all 3 groups. All right, and then our alternative is just going to be the opposite. So the distribution of concussions is not the same for all 3 groups. For all 3 groups. Okay. So that is our first step to set up the hypotheses in sentences. Okay, so the next one is we're going to go ahead and find our conditions. All right, so we want to check to see if it's a random sample. And let me see. They don't, oh, it does say. All right, so random sample is given to us. Great, so we have random sample for our first condition. Okay, for the second condition, we're going to go ahead and need to check those expected counts. Now, I'm not going to have you guys do this whole thing for every single cell. That would take forever. Oh, where did my random sample go? Random sample. Because your calculator can actually find the expected counts for you. Okay, so this is going to be a little tricky since I can't actually show you my TI. So I'm going to write down the buttons and hopefully you guys can follow along. Okay, so to find the expected counts, the first thing you're going to do, and let me write this down. Okay, is you're going to do second, and then the button that has x to the -1 above it, it says matrix. All right, so once you do second matrix, you should see names, math, and edit at the very top. Go ahead and move to the edit. So go 2 to the right, and then it should give you matrix A, and then you have some dimension, something, a number by a number. All right, so in this example, we have, not including the totals in the margins, this is a 3 by 4. So change the dimensions to a 3 by 4, and then go ahead and input those values into your matrix. All right, so it should look just like that table, but in your calculator. All right. Now, once you've done that, you're going to go to Stat, and you're going to move to Tests, and you're going to scroll to C, which just says chi-square test. And in it, you should see observed, and matrix A is already in there, and expected, matrix B is there. And that tells you that they're going to put the expected counts into matrix B. So you don't have to do anything here. You just scroll down and press calculate. All right. Now, just to double check, I get a chi-square of 22.0285. All right, but we're not going to do anything with that just yet, because right now, again, we're just trying to check that second condition. All right, so what you need to do is you need to go back to second matrix, move over to edit, scroll down to matrix B, and press enter. And when you're looking at matrix B, you want to look at those numbers and make sure that they are all greater than or equal to 5. That is our condition. So in this case, if you notice, there are actually a couple that are not greater than or equal to 5. Those last two in the last row are not greater than or equal to 5. So we did not meet that condition. All right. So at this point, we actually need to fix the problem. We're not going to give up. We're going to fix the problem. So how you fix the problem is you can actually combine columns or rows to make it so that those expected counts are greater. So in this example, since these last two are the ones that cause the problem, all right, these last two, I'm going to go ahead and I'm going to combine these two columns together. Because contextually it makes the most sense to combine 2 and 3 or more to be 2 or more. All right. You could possibly combine these two, non-soccer players and non-athletes, but I think it makes more sense to do it this way. All right, so what we're going to do now is we're going to check and make sure that if we combine those, we will get our expected values that we need. Okay, so I'm going to combine those. So now this guy, instead of being two separate numbers of 11 and 10, this now combines to 21. This combines to 13, and this combines to 3. Okay, so let's go back. We are going to go back to second matrix, and we're going to move to edit. And now we're going to change the dimensions. So press enter on matrix A, and now we're going to change the dimensions to a 3 by 3 since we're combining two of those columns. All right, so the first two columns should still be the same. Now the last column, instead of 11, 8, and 3, should say 21, 13, and 3. Okay. And now we're going to do this step again. We're going to go back to chi-square test. So go stat, move over to test, go up to letter C. Remember, you don't have to do anything in here, just scroll down to calculate. And now I get a chi-square of 20.6036. I'm not going to use that yet because right now I'm just looking to see my matrix B. I just want to make sure that those expected counts are greater than or equal to 5. So go back to second matrix, move over to edit, scroll down to matrix B, press enter, and check out those numbers. All right, and it looks like all 9 of those are greater than or equal to 5. So that is what we're going to work with. Okay, so all of that was to check that second condition. And you're not always going to need to combine, just sometimes. So I just wanted to show you what that would look like. All right, so let me go ahead and erase some of this and get back to our problem. All right, doesn't seem like I can erase, so I'll just continue down here. Okay, so ignore all that now. Okay, so our second condition is that all expected counts are greater than or equal to 5 now. All right, and data are in counts. Okay, all right, let's move on to statement. So statement is that I will use a chi-square model with, now remember we changed the dimensions of our table. We have a 3 by 3 now. And so to find degrees of freedom, you subtract 1 from each of those numbers and multiply. So 3 by 3 minus 1 gets me 2 times 2, which is 4 degrees of freedom. To do a chi-square test for homogeneity. All right. So chi-square test for homogeneity. Okay, and now we can go back to stat, test, letter C, chi-square test. Don't do anything in there, just go ahead and press calculate, and that will get you your chi-square and your p-value. So I got a chi-square of 20.604 and a p-value of 0.000379. All right, or you can write 3.79 times 10 to the negative 4. That works too. All right. So our final conclusion, since our p-value is super small, we're going to go ahead and reject the null hypothesis. So since the p-value is so low, we reject the null hypothesis, which means that there is enough evidence to suggest that, and then you can just copy your alternative hypothesis sentence, that the distribution of the number of concussions is not the same for the three groups. Okay, and that's how you do it. All right, so let's go ahead and I'll show you another example. If you think you got it, go ahead and just pause the video and then fast forward to the end and you can check your answer. Or if you just kind of want to hear another explanation one more time, you can go ahead and listen through the video for the second example. All right, so example number 2 says medical researchers enlisted 90 subjects for an experiment comparing treatments for depression. The subjects were randomly divided into 3 groups and given pills to take for a period of 3 months. Unknown to them, one group received a placebo, the second group the natural remedy, St. John's wort, and the third group the prescription drug Prosrex. After 6 months, psychologists and physicians who did not know which treatment each person had received, so it was a double-blind experiment, evaluated the subjects to see if their depression had returned. All right, so let's go ahead and start with the null and alternative hypothesis. All right, so the null hypothesis, I would say the distribution of depression recurrence is the same for all 3 treatments. And alternatively, the distribution of depression recurrence is not the same for all 3 treatments. Okay. Secondly, let's check the conditions. So this one, the subjects were randomly divided. They weren't randomly selected, so I'm going to call this random assignment. All right, and then my next check is to make sure all expected counts are greater than or equal to 5. So I'm going to move on to my calculator. I'm going to go second matrix, edit, enter on matrix A, this is a 2x3 matrix, and I'm going to type in those values. All right, moving over to stat, test, letter C, chi-square test, calculate, and then back to second matrix, edit, and then select matrix B. And double checking those numbers, I see 20, 20, 20, and then 10, 10, 10. So all expected counts, those are the expected counts in matrix B, those are all greater than or equal to 5. So I can say all expected counts are at least 5. And data are in counts. Okay. So step 3, I got my statement. I will use a chi-square model with, all right, so this is a 2x3. So if I do -1, I get a 1/2. So that gets me 2 degrees of freedom. To do a chi-square test for homogeneity. All right, so now I need my chi-square and I need my p-value. So going back to stat tests, letter C, chi-square test, and I get a chi-square of 8.4, p-value of 0.015. Okay, so pretty low p-value. So I'm going to say, since my p-value is so low, I reject the null hypothesis, which means there is enough evidence to suggest that, I'm going to copy my alternative, the distribution of depression recurrence is not the same for all 3 treatments. All right, and that is it. And I mean, if you wanted to go back and look and see, well, which one did best, definitely if you were to recommend treatment, it seems like Prosrex did the best job. All right. Okay, and that's it for lesson 2.